All right, let's take a look here. Let's see if we can identify some functional groups in these molecules. So the one with this one over here, if I call this one A, could anybody identify any functional groups in this molecule? Yeah, there's definitely an amine. There's an alcohol. Yeah, absolutely. Yeah, both 100% correct, right? So here we have an amine. This is an amine. What else? We got alcohol, aromatic. Yes, so we have an alcohol over here. So we have an alcohol here. Somebody said an aromatic. Yes, this is an aromatic. Right here, aromatic. Or in the textbook, it says sometimes they're called arenes, which is also fine. Yeah, good. There's the last one, which is an ester. Absolutely. So this one here is an ester, right? So we have an ester. Because remember that an ester, we have a carbonyl, then we have an oxygen, and we have two R groups, right? They might be the same, they might be different, but this counts as an R group here, and this counts as a different R group over here. So this one is an ester, right? When you're identifying functional groups that have carbonyls in them, you kind of have to do the 30,000-foot view. Somebody's asking, is there also an ether? So I'm assuming that you mean, or you're wondering, would this be an ether? Okay, and the answer is no, that is not an ether. Like I said, you have to do the 30,000-foot view. You have to look at the entire thing. An ether is when we have two R groups and an oxygen in between them, right? That's an ether. So if we have an R group attached to an oxygen and then we have a carbonyl next to it, that's an ester. All right, there we go. What about the one on the bottom right? Can anybody identify any functional groups in this guy? Yes, there's a ketone, absolutely. So here we have a ketone. What else? Aldehyde, yes. This is an aldehyde here. Absolutely. A sulfide. So this isn't a sulfide. This one here is a thiol. So this is a thiol. A sulfide is when you have a sulfur sandwiched between two R groups. Okay, that's a sulfide. There's two more. I'm looking to see if anybody's typed them in here. Yes, Mackenzie, absolutely. This one here, this is an ether. All right, so if I want to circle the whole thing, this would be the ether here. All right, there's an ether, and then there's one more functional group in here, an alkene, absolutely. So here we have an alkene. And there you go. We've identified a whole bunch of cool functional groups in these two, big molecules. So of course you're going to be asked to identify functional groups in molecules on your second quiz for sure. The quiz that covers chapter 2. All right, well, let's get back into it here. And we left off somewhere around here around functional groups. And now we're going to talk about carbon atoms with formal charges. All right, so let's get to it. A carbon atom with a formal charge. Now we talked about carbon having 4 bonds. When carbon is sp3 hybridized and it has 4 bonds, it has no charge, right? If you calculate the formal charge, 4 valence electrons, subtract 4 sticks and 0 dots gives you 0. So a carbon with 4 bonds has no formal charge. But when carbon has a positive charge on it, we call it a carbocation. Carbocation. It's going to have 3 bonds, and it will be sp2 hybridized, which means it has an empty p orbital. So if we take a look at this bond line structure here on the far left, you see that we have a carbocation here. Now, the only way that you would know that this is a carbocation and that it's not just, this, and that we assume that there's a hydrogen attached here, the only reason that you know that there's no hydrogen attached to that carbon is because they put the positive charge there. So you have to include the positive charge to tell the reader that this carbon is sp2 hybridized, okay, and is a carbocation because the p orbital is empty. Same thing over here. Now this carbon has a positive charge. It's a carbocation, but we know that carbon will have 3 bonds when it is a carbocation. So we know that there is 1 hydrogen attached here. Again, we know that the carbon is sp2 hybridized and has an empty p orbital. And then lastly, if you were to have the carbocation on the end of a bond line structure, we know that there are actually 2 hydrogens attached here, right? Because when we have the sp2 hybridized carbon, the carbon must have 3 bonds. And so the same rationale applies for each time for all of these sp2 hybridized carbons, is that they always have 3 bonds. And so based off of the type of carbocation, you can infer how many hydrogens there are on the carbon. Now, besides a carbocation, we can have a carbon with a negative charge, and we call that a carbanion. A carbanion, carbon will be sp3 hybridized, and in the it will have an extra electron. So if you think about the formal charge here, we have 4 valence electrons, subtract 3 sticks and 2 dots, which gives us -1. I didn't do it for these ones up here, but we can do the same thing. We have 4 valence electrons, subtract 3 sticks and 0 dots, gives us +1, right? Same rationale applies both ways in terms of calculating formal charges for carbocations and carbanions. So formal charge affects the stability and reactivity of molecules, and so you've got to be quick, quick at identifying formal charges in molecules, because that's the whole point, is that we want to be able to assess the stability and reactivity of molecules as the course progresses. Let's take a look at this molecule that's shown here on the screen, and let's see if we can fix this molecule by including formal charges. So I'm going to give you a second to take a look at this. And if anybody could just tell me an atom in here that has a formal charge or describe it to me. Are there any formal charges in here? I'll give you a clue, there are. I'll give you a second. Could anybody identify one of the formal charges or a couple of them? So Warren is saying oxygen. There are 3 oxygens in the molecule. Which one? Right? If I call this one, if I call this one A, if I call this one B, and I call this one C, which one would have a formal charge? The one on the left side. Okay. Allison says the nitrogen on the far right. Okay. I agree with that. Now, what would the charge be on the nitrogen on the far right? So this nitrogen here, what kind of formal charge does it have? It's got a +1 formal charge, doesn't it? Right? Because if you take 5 valence electrons, subtract 4 sticks and 0 dots, what do you get? +1. Absolutely. So we're good on that. We got a +1 charge on our nitrogen. Now, Warren said that there's a charge on this oxygen over here. He's absolutely correct. We can do the same rationale here. We say this oxygen has 6 valence electrons, subtract 3 sticks, 2 dots, +1. So this oxygen has a +1 charge. Absolutely. Absolutely. And there's one more formal charge in here, and that is on this oxygen right here, right? We have 6 minus 1 stick minus 6 dots. That's not supposed to be an equals. That was supposed to be a subtraction, and we get -1. So there's a -1 charge over here on this oxygen. And those are all of the formal charges in this molecule. There are no other formal charges. You might think, oh, maybe there's a formal charge on the sulfur or something like that. Well, you can take a look. If we look at the sulfur, sulfur has 6 valence electrons, subtract 4 sticks and 2 dots, gives us 0. So the sulfur has no formal charge, and none of the other heteroatoms have any formal charge on them. So we were able to identify formal charges pretty quickly, I think. And with that in mind, let's take a look at some patterns that we can use to identify lone pairs on nitrogen, oxygen, and carbon when they have charges. So it says oxygen has 3 possible bonding patterns, the same 3 patterns for any second row atom with 5, 6, or 7 valence electrons. So 5 would be a nitrogen, right? 6 would be an oxygen, and 7 would be a halogen, would be fluorine. Anyhow, there we go. So let's see. When oxygen has 7 valence electrons, it's got an extra electron, and so it's going to have a negative charge. Right? If you look at the 2 examples here, Whenever oxygen has one bond and 3 lone pairs, it's going to have a -1 charge. I'm not going to do this for every single situation here, but same thing. 6 minus 1 stick and 6 dots equals -1. When oxygen has 2 bonds and 2 lone pairs, like in a water molecule or in this ethanol molecule here, the oxygen has no charge. And finally, when oxygen has 3 bonds and 1 lone pair, it will have a +1 charge. Look, 6 minus 3 sticks, 2 dots, +1. There we go. So what you're going to find is that over time, you're going to recognize these bonding patterns immediately. And you'll be able to look at this very quickly and say, that oxygen is going to have a negative charge, right? This oxygen will be neutral, and this oxygen will have a positive charge. You'll see it come up so many times in organic chemistry that you will get very quick at identifying formal charges on atoms. What about a nitrogen? There's 3 bonding patterns for a nitrogen. Nitrogen has 5 valence electrons. It's in group 5A. So when it has 6 valence electrons, it's going to have a negative charge. So whenever you see a nitrogen that has 2 bonds and 2 lone pairs, it's got a -1 charge. Whenever we see a nitrogen with 3 bonds and 1 lone pair, it has no charge. And just like we saw in that last molecule, like Allison pointed out, we had a nitrogen with 4 bonds and no lone pairs. It has a +1 charge. And so again, you're going to get more accustomed to seeing these, over and over and over, and you'll be able to identify formal charges on nitrogen. Trust me, you'll get very quick at it. All right. And with that in mind, let's see if we can identify some lone pairs on some of these molecules and ions. So if we start with E, you see that we have an oxygen with a negative charge. So if I redraw the ion over here, okay, if the oxygen has a negative charge on it, the lone pairs are left out. Oftentimes we leave lone pairs out in organic chemistry, but can anybody tell me how many lone pairs there should be on this oxygen atom in order for it to have a -1 charge? Exactly, it should have 3 lone pairs. 1, 2, 3. Right? Why? Because when you take 6 minus 1 stick and 6 dots, it gives you -1. All right, if we move over to the next one, this is an ether. Okay, you can see that the oxygen has no charge on it. Can anybody tell me how many lone pairs are missing on this oxygen in F? How many lone pairs are missing on this one? 2, absolutely, because when oxygen has 2 bonds and 2 lone pairs, it has no formal charge, right? 6 minus 2 minus 4 gives you 0, absolutely. Last one, G. You see that the oxygen has a positive charge on it, +1. So it's got 3 bonds. How many lone pairs must it have? The lone pairs are left out, but we know exactly that there must be 1 lone pair on it. Why? Because 6 minus 3 sticks minus 2 dots gives us +1. And so oftentimes we'll see atoms that have charges, oxygen, nitrogen, carbon. The lone pairs will be left out, and we have to be able to fill in the lone pairs because lone pairs are going to be very important when we start to draw mechanisms later on in the class, and also when we start to draw what are called resonance structures in this chapter. All right, well, I told you that chemists have lots of different ways to represent molecules. We have lots of different ways to draw their structures. We looked at condensed structures, partially condensed structures, Lewis structures, molecular formulas, and bond line structures. And now we're going to talk about a 3-dimensional representation of molecules using bond line structures. Because we know that molecules, if you've got a molecular model kit, and if you've ever made a molecule with your model kit, you know that molecules are 3-dimensional objects, aren't they? Right? They take up space in 3 dimensions. Therefore, it's difficult to represent a 3-dimensional molecule on a 2D piece of paper or a blackboard or an iPad screen. And so how do we represent the 3-dimensional nature or structure of molecules? Well, sometimes we use what are called dashes and wedges. When we draw a dash, and this is a dash right here, what the dash means is that the bond is going into the paper or into the screen or into whatever plane that you're looking at the molecule on. It's going in. And when we have a wedge, it's a solid line like this. So this is a wedge. It means it's coming out towards us. The shadow implies that it's coming towards us. And so we can have an acyclic structure. We can draw dashes and wedges there. So the wedge, again, means that this hydroxyl, for example, is coming up or out towards you, right? And this dash means that this hydroxyl or this alcohol functional group is going down, right? It's pointing into the screen or into the page. We can also use dashes and wedges to represent what are called bicyclic molecules. So this one's kind of an interesting molecule. You have a 6-membered ring. I'll trace it for you in yellow. So there's 1, 2, 3, 4, 5, 6 carbons in a ring. But you also have a 5-membered ring in here. Look, you have 1, 2, 3, 4, 5. So this is a bicyclic structure. And what they're trying to show you here, I'll do my best to draw this, is that you have the 6-membered ring like this, okay, and then you have the 5-membered ring on top like that. Then you have a bromine pointing up like this, and then you have that CH3 pointing down like this. And if you're wondering what the heck is that, okay, well, I'm going to show you how to draw bicyclic structures later on in the course. But the idea is that this bridge, this is what we call a bridge, oops, the bridge is coming up, right, because it's on a wedge. This one is pointing up and this one is pointing down. Give me a thumbs up if you follow me on the concept of a dash and a wedge. All right, thanks, Kyla. Good, good. Dashes and wedges. Well, you can imagine that organic chemists can't stop there. There are other ways that we use to represent 3D structure. I just showed you the bicyclic structure. I tried to draw one the best I could. We also use what are called Fischer projections. These will come up more in organic chemistry too. However, we do look at them in organic chemistry 1, especially when we discuss stereochemistry in chapter 5, which is coming up. Fischer projections were developed by Emil Fischer, and the reason why he came up with the Fischer projection was because he was classifying all the different carbohydrates, and there's so many carbohydrates that actually Fischer projections are easier ways of looking at them. The next one is a Haworth projection, sometimes pronounced a Haworth projection, depending on who's saying the word. I call it the Haworth projection. I like Haworth projections. We only use them for cyclic compounds, and it just helps you visualize which groups are above a ring and which groups are below the ring. So what's being represented in this Haworth projection here is that you have a 6-membered ring like this, and then you have the hydroxyl from the alcohol pointing up, right? Because it's going up here, so it's up here, right? That's what the wedge means. And then you have the bromine going down like that. So that means the same thing. And the reason why 3 dimensions, or the three-dimensionality, I guess, of a molecule is so important is because it's going to govern how the molecule interacts biologically, right? If you take a look at the Medically Speaking, I think it goes into some detail about receptors and molecules and how they bind to receptors. And so we could talk about this all day, and we'll talk about it more in chapter 5. But the 3-dimensionality of a molecule is very important in terms of its biological activity, because our bodies are 3-dimensional structures. Anyhow, from there, we're going to move on to section 2.7, which deals with the concept of resonance. This is something that you should have seen in General Chemistry 1, and we're going to cover it in detail here, and we're going to take a look at drawing resonance structures in this chapter as well. So follow along with me. It says pi bonds and or formal charges are often more spread out than a bond line structure can imply when we just take it at face value. Consider this carbocation right here. This is called an allyl carbocation, this thing right here, okay? In this case, the pi bond and the positive charge are inadequately described by the bond line structure. Now, there is nothing wrong with this bond line structure, okay? There's nothing bad about it. What it's saying is that it's an inadequate description of the allyl carbocation. That's another way of saying it doesn't tell the entire story, right? There's something missing here, okay? And the reason that there's something missing is because of this. There is a p orbital on each one of these carbons, right? Carbon 1 and carbon 2 are both sp2 hybridized, aren't they? Right, so that means they all have, or they both have three sp2 hybrid orbitals, but they also have a p orbital. I'm going to draw the p orbital here, and I'm going to draw a p orbital here. Now, carbon 3 is a carbocation. What do we know about carbocations? We just discussed them. Carbocations are sp2 hybridized, and they have an empty p orbital. Okay. So what happens is that these three p orbitals, and I don't have the perfect drawing here. I'm going to show you a much better representation on the next slide. All three of these p orbitals overlap. Okay, and what that does is it forms basically a conduit, or like a tube, where the electrons that are in the pi bond here, they can travel between all three. Okay, so they can reside between all three of those p orbitals. So again, since each one of those carbons has an unhybridized p orbital, all three of those p orbitals can overlap side by side. So what happens is those electrons in that pi bond, they're allowed to move all around that overlapping area, right? They can be anywhere inside this conduit, right? Which is formed by the overlapping of these unhybridized p orbitals. What does that mean? If those electrons from that pi bond are free to move between the three p orbitals, that means that they are delocalized. They don't reside in one specific area. If you go back to this structure, right, it looks like they're just residing right here. But we know that this doesn't adequately describe the situation because of the three overlapping p orbitals. Let's take a look at it even deeper. Okay, so we say that this molecule has resonance, and we use the term resonance, which simply means that we have delocalized electrons. Now, how would we more adequately describe the allyl carbocation, since our first picture didn't adequately describe it? The way that we do it is we use what are called resonance structures. So it says here the pi electrons can exist on both sides of that central carbon, so we can draw two different resonance structures to represent the compound. It's important that you understand that the molecule, or I shouldn't say the molecule, the ion is not vibrating back and forth, okay? What it means is that when we have this double-headed arrow here, this is called a resonance arrow. So this is a resonance arrow, not to be confused with an equilibrium arrow, right? This is an equilibrium arrow. This is something completely different. Okay, we're not talking about equilibrium. We're talking about resonance. And these square brackets, which we put around our resonance structures, tell us that we're dealing with one entity, okay, which is described by both of these resonance structures. All right, so both of these structures are describing one compound, or one allyl carbocation. Because neither of these resonance contributors actually exists, okay, and for that you'd have to look at the molecular orbitals, we can use what's called a resonance hybrid to describe the allyl carbocation. So instead of having the pi bond shown on one side like it's localized here, and then on the other side as if it was localized there, we can kind of make a broken pi bond like this dashed line, and then instead of having a full-on carbocation here and a full-on carbocation there, we just say, well, both ends are partially positive like this. Look, I'm going to tell it to you straight. I'm never going to ask you to draw a resonance hybrid. Now, normally when you say stuff like that to students, and I was a student for a long time, I just think, all right, don't need to know it, okay? Now, if you look at the suggested practice problems that are posted to Canvas, you'll see that I included questions that deal with the resonance hybrid, even though I told you I'm not going to ask you about it on the quiz. Now, you're probably thinking, why the heck would you do that? I'm just going to skip it if you're not going to ask me about it. The reason why is because even though I won't ask you directly about the resonance hybrid, they are really helpful for your understanding of resonance structures. So again, these resonance structures are not switching back and forth. Now, depending on the organic chemistry textbook that you look at, and there are many different organic chemistry textbooks out there, there's all kinds of funny analogies for resonance structures. Just remember, the resonance structures are not switching back and forth. Both of these are used to represent one thing, which can be kind of represented by the resonance hybrid. The example that he used in the textbook, and I've seen, ones where they describe, what is it, like a donkey and a horse breed to make a mule, which is a hybrid of the two. But the one that's in our textbook is the nectarine. So if you've ever had a nectarine is a hybrid of a peach and a plum. But if you look at a nectarine, like, it's not a plum one second and a peach the other, right? It's just a nectarine all of the time. It's a hybrid of the two. And that's what, how a resonance hybrid can help us a little bit. Now, again, you will be asked to draw resonance contributors. However, you will not be asked to draw resonance hybrids on a quiz. All right. So the more electrons are spread out, the lower energy the ion or molecule is, and it basically stabilizes it, right? I told you that electrons are like hyperactive children. They like to move. If they can move, they will. And so the more resonance contributors we have, the more stable our molecule becomes. All right. The delocalization of charge, it says here the charge is spread out over more than one atom. The resulting partial charges are more stable than a full-on +1 charge. Well, with all that in mind, let's switch gears for a bit and let's talk about what are called curved arrows, because we need curved arrows to enable us to draw resonance structures. Now, I've taught general chemistry for a long time, and I always introduce my students to the concept of resonance in general chemistry, and we usually draw the resonance structures of the carbonate ion, let's say. However, I usually don't ask my students to draw curved arrows in general chemistry, so I'm sure this will be new for most people. All throughout Organic Chemistry 1 and Organic Chemistry 2, we use what are called curved arrows to represent electron movement. And a curved arrow has a tail and it has a head. A curved arrow looks like this, okay? We call this part the tail, we call this part the head, as you can see over here. And when we have a double-headed arrow in organic chemistry, the double head represents the flow of 2 electrons, okay? Later on, we'll look at single-headed arrows, which we call a fishhook arrow. That represents the movement of 1 electron, which is, produces a radical, but that's neither here nor there right now. We'll look at that at the very end of the semester, so let's not worry about it today. So again, these curved arrows represent the movement of pairs, or 2 electrons at a time. The arrow starts where the electrons are currently located, and they end up where the electrons will end up after the electron movement. We're going to take a look at curved arrows to show reactions in Chapter 3. In this chapter, we're not going to take a look at curved arrows to show reactions, but we will use them to represent, or to enable us to represent resonance structures. So there are really specific rules for using curved arrows to describe electron delocalization or resonance. Follow along, and we'll go through all the rules here. The first one is never show a single or sigma bond as being delocalized. So in other words, don't break a single bond. Will we break bonds with curved arrows? Yes, but only when we're discussing reactions, and we are not discussing reactions in Chapter 2. Hear ye, hear ye. We are not discussing reactions here. So we're not going to break any single bonds with a curved arrow in this chapter. What else? Single bonds break in a chemical reaction, but not resonance. All right. Never exceed an octet for a second row element, right? This is something that you learn in general chemistry, and we talked about it in Chapter 1, right? Second row elements only have the s and p orbitals available to them. 2 electrons in an s, 6 electrons in the p orbitals. 2 plus 6 is 8. And so you can only have an octet of electrons for second row elements. The valence shell of a second row element only has 4 orbitals, therefore 8 electrons. So all of these curved arrows are wrong. I love this. Bad arrow. Okay, these are all bad arrows because they violate the octet rule. Now, normally I don't take the time to draw, what would result from drawing these curved arrows because they're bad, right? They're wrong. But let's say, for example, there isn't a lot of room here. Let's say you drew what you would get from this curved arrow, right? Remember, the tail of the arrow is starting on this lone pair, and it's ending up in between the oxygen and the carbon. Well, what's a pair of electrons between 2 atoms? It's a bond. So what you would get from this would look like this. You'd have the oxygen, you'd have a double bond to the carbon, which would have 3 hydrogens. Don't write this down, okay? Don't copy this. And then you'd still have 2 lone pairs left over here. What is the problem here? What is my major malfunction here? Could anybody tell me? There's something that's just so wrong here. Hold on, I'm trying to see. Yes, thanks, Kyla. Absolutely. The old Texas carbon here. Bad arrow, right? Really, really bad. Never draw that. I mean, you get the same thing here. You'd end up with a nitrogen that has 4 bonds in a lone pair. It would be surrounded by 10 electrons. Should I draw these? I don't know. They just feel wrong. I don't like drawing things that are wrong in front of my students. Maybe it's a teaching moment. I'll draw one more just to show you again. If you were to draw the result of this arrow, you'd end up with this. Now you have a nitrogen surrounded by 10 electrons. That is just plain old wrong. Okay, same thing here. You'd exceed the octet rule for this oxygen. And then what's this one? You'd exceed the octet rule for this carbon here. So those are all bad arrows. So don't violate the octet rule. What else? Second row elements can have less than an octet. Absolutely, they can have that. But they can't have more than an octet. So here's acetone. We actually saw this molecule several times already throughout the class. This curved arrow isn't bad. Okay, you end up with 2 charges in this resonance contributor. The carbon doesn't have an octet. It's a carbocation. The oxygen does have an octet. Don't be fooled into thinking, I've seen students do this before. They'll say, well, the oxygen has a negative charge, therefore it doesn't have an octet. It's got extra electrons. That's not true. It's still surrounded by 1, 2, 3, 4, 5, 6, 7, 8. It still has a complete octet. It just has a negative charge, right? It's got an extra valence electron. Anyhow, there we go. What else? What other rules do we have here? Well, let's use the rules. All right, if there's one thing I've learned teaching chemistry, it's that science students, and I was one for a long time, and I'm still a science student. Science students, we all kind of enjoy rules, don't we? We all like rules. Okay? I have so many science students who are just like, tell me the rules, Mr. Dion, and I'll learn them, and then I'm going to apply them. All right, and then I'm going to understand what's going on, and you're 100% right in assuming that. This is kind of a funny question. In each of the following cases, determine whether the curved arrow violates either of the 2 rules and describe the violation, if any. Don't forget to count all hydrogen atoms in lone pairs. So I'll just ask you about A. Is there a violation here, yes or no? If anybody could just tell me, is this a violation? Is this a bad arrow? Yeah, thanks, Mackenzie. Kyla, both of you are 100% correct. Major violation here, right, Jonathan? Yes, Benjamin, all correct. You're all 100% correct. If you draw what you would get here, let me get a better color pen here. I mean, again, don't even write this down. This is just garbage, right? And I don't like to talk like that, but, you know, my students wouldn't do that, okay? You'd end up with something that looks like this. You'd actually end up with a positive charge here. But then you've got your nitrogen surrounded by 10 electrons. So that is just plain wrong. What about B? Is there a violation here? Yeah, so I'll write that down, Jonathan. So violates octet rule, absolutely. What about the second one? Is there a violation in the second one? Absolutely, Benjamin. No violation whatsoever. Right? There's no problem here. Okay, if we draw the resonance contributor, you'd end up with, you'd get this. You'd have a negative charge on the oxygen, a positive charge over here. I'll draw my resonance brackets. There we go. And what about the next one? Is there a violation in C? Cha or no? Cha-cha? No. Anybody? Mackenzie says yes. Benjamin says no. I say there is a violation. Let me show you why there's a violation. This one's a little trickier, I think. It's because you got to remember there's a hydrogen here, right? If you were to draw that resonance contributor, it would look like this. You'd have, and then you have this and this, right? You'd end up with a positive charge over here, and then anyhow, let's leave that out. But the idea is that you'd end up with a Texas carbon, right? So violates, where's my red pen? Violates octet rule. All right. By the way, you guys, thanks for answering any of my questions. I really appreciate that when my students are eager to answer questions. Makes me happy. What did I want to do here? Copy and paste. There we go. So both of those violate the octet rule. Bad arrows, crummy arrows, ridiculous arrows. When using curved arrows to show resonance, the structures will often carry a formal charge that's got to be shown. Let's give this one the old college try and see if we can draw what we would end up with. Look, let's draw everything that doesn't change. So we have this oxygen, we have this carbon, and this carbon. if you look at the first curved arrow, you took a lone pair of electrons and you made a new bond here. So look, we're going to have a double bond here, and we're going to still have this lone pair up here. Now the second curved arrow, you took the electrons from the pi bond, right? Now this is a trick I don't want you to fall into. You see where the tail of this arrow starts? It looks like it starts on this sigma bond here, but it's actually starting on the pi bond, right? The pi bond is the weaker bond, so those are the electrons that are going to move. So we're taking that pair of electrons, right? There's two electrons in a pi bond. You're taking them and you're putting them right on this carbon. So now you've got a pair of electrons here. Now there's going to be two formal charges in this molecule. Could anybody, and I know it's not easy on Microsoft Teams, believe me, I'm not that crazy. Could anybody tell me where the formal charges would be and tell me what they would be? And again, I know it's not easy on Teams, but do your best to describe it. Absolutely, Kyla, 100%. Yes, yes, yes. Okay, good. Everybody get the oxygen. Everybody's killing the oxygen. Okay, you guys get that 100%. Now, let's think about this. If there's no charge over here, that means that this has to be neutral as well. And I see that somebody figured it out. Somebody says there's a -1 charge on the carbon, and that's 100% correct. Remember, there is a proton on here, right? There's a hydrogen on here. Okay, so you've got 1, 2, 3 bonds in a lone pair, so that's a -1 charge, isn't it? And on my oxygen, I have 3 bonds in one lone pair, so I have a +1 charge. Boom! All right. Why is it not a double bond on the lower? I'm not sure how you would get a double bond, right? What we're doing is we're taking this pi bond here, we're taking the pair of electrons, right? A bond represents 2 electrons, and we're taking them, the head of the arrow is not ending up between atoms, right? When you make a bond, the arrow will end, this arrow is ending between an oxygen and a carbon, so you're making a bond, right? This arrow is ending right on a carbon, so the pair of electrons ends up on the carbon. Does that answer your question? Yes, only electrons are moving. All right, there we go. Does that answer your question? All right, well, from there, let's move on and let's talk about resonance pattern recognition. Section 2.10, resonance pattern recognition. Like I just told you, you know, science students like rules, and I don't blame them one bit. Like I said, I was a science student for a long time, and I am still a science student, and I like rules too. And so when I studied organic chemistry, back in 1995, the textbook that I used, there's a textbook that my university used, had no rules like this. This is kind of a David Klein thing, the author of our textbook, but there's a reason why our textbook is the most popular organic chemistry textbook in America. Is because of these things, like these rules, which are really, really handy for students. So what we're going to do now is I want to take a look at these rules, and then we'll take a break. Now, it's going to take us a few minutes to get through the rules, but before we could, try some good resonance practice problems, we got to take a look at the rules. So here we go. It says there are 5 general bonding patterns in which resonance occurs. You got to be able to recognize these patterns in order to be able to predict when resonance is going to occur. And we'll look at each one of them in detail. First one is an allylic lone pair. Second one is an allylic carbocation, a lone pair of electrons next to or adjacent to a carbocation, a pi bond between 2 atoms with different electronegativities, and conjugated pi bonds in a ring. So we have an example of each one of them, but let's get into them in detail. The first one is what? The allylic lone pair. So the first thing we got to do is define what is called a vinyl and an allyl position in a molecule. So the vinylic position and allylic position refers to when we have a carbon-carbon double bond, the carbons that are involved in the double bond, these are called the vinylic positions. Okay, so the actual carbon, that position is called the vinylic position. If you go 1 carbon away, these are called the allylic position. So we're going to talk about an allylic an allylic lone pair and an allylic carbocation. So you have to understand what allylic means, right? So when you have an allylic position, look, this is what you look for. You look for the position here, then you have a bond, then a double bond. Okay, so that means that that carbon is allylic, right? Single bond, double bond, it's allylic. Look, if we look at this example down here, it says we look for allylic lone pairs because they're resonance delocalized. The reason this lone pair is not allylic is because it's not allylic to a pi bond. If we look at this lone pair, it is allylic to a pi bond. Why? Because it goes lone pair, single bond, pi bond, right? So they're allylic to the lone pair, right? If this is our double bond, I'll repeat myself here. These are vinylic positions. This is an allylic position, and this is an allylic position. There's a lone pair on this nitrogen, which is in an allylic position. So we call that an allylic lone pair, and it will participate in resonance. Okay, all the lone pairs in these molecules and ions are examples of allylic lone pairs. Two curved arrows have to be used to show the resonance delocalization of the lone pair. So let's start with the first one. We have an allylic carbanion. So how would we show the resonance of this? We're going to take that lone pair. We're going to make a new pi bond here in between this carbon and this carbon. And then we're going to take this pi bond and we're going to put a pair of electrons over here so that we end up with this resonance contributor, like this. How do I know that's an allylic lone pair? Again, this is a vinylic position. This is an allylic position. There's a lone pair on it, therefore it's an allylic lone pair. Let's try it again. Look, here we have our double bond. This is an allylic position. This is an allylic position. The oxygen just happens to have lone pairs on it. So those are allylic lone pairs. Therefore, we can draw curved arrows and show a resonance contributor. So we make a new pi bond, we break this pi bond, and we put the lone pair down here, and we end up with this resonance contributor. So where we have a positive charge here, and we have a lone pair and a negative charge over here. Same thing. I'm just repeating myself over and over like an old man. Here we have a pi bond. Single bond, this is an allylic position. There are lone pairs. Walla walla bing bang. We can draw a resonance contributor. We draw a new pi bond being formed, and we put this lone pair up here. There was already a pair of electrons on here that weren't drawn. And we end up with a new resonance contributor, which looks like this. So we have a lone pair, 3 bonds. We have a positive charge here. And this oxygen now has 3 lone pairs and has a negative charge. The last one, again, they've left out a pair of electrons that should be here. Or no, it's not the last one, sorry. We have a pi bond, right? This is an allylic position. This is an allylic position. This is an allylic position, but only one of them has a lone pair, and it's this one. So we take it, we form a new pi bond, we break this pi bond, and we put the electrons up here, allylic lone pair. So we draw the resonance contributor that we end up with, which will look like this. There we go. So now we have the negative charge up here. And we'll do the last one. This is an amide, and we'll show how there's a resonance contributor here. So we do this. There's a lone pair missing. Okay, and we'll break this bond like that. Oops, there we go. And now we draw the resonance contributor, which looks like this. And there you have it, my friends. An allylic lone pair. Give me a thumbs up if you follow me on the concept of an allylic lone pair. Same pattern over and over and over is what we looked at here. 5 different examples of an allylic lone pair. All right, we covered what a vinylic position is, what an allylic position is. If you have a lone pair on an allylic atom, it's going to have a resonance contributor, and I showed you how to draw them. You need 2 curved arrows. Each one of these had 2 curved arrows in it, right? All right, let's move on from there. When the atom with the allylic lone pair has a negative charge, the charge gets delocalized, so we saw that. If the allylic atom is neutral, it's going to become positive, and the atom receiving the lone pair will become negative. Now, these are just rules. I mean, I think it's just easier to tally up the formal charges yourself, or become accustomed to them and be able to recognize them fairly quickly. All right, what's next? The allylic carbocation, which we already saw. You only need one resonance arrow to draw this. You can see how you just move the pi bond electron. So here are the electrons from the pi bond. Right here, we move those over, and we make a new pi bond, and now this carbon is going to be electron deficient, and so it becomes a carbocation. What's cool is if you have multiple double bonds in an ion like this, okay, you can draw multiple resonance contributors. So you see, you move this pi bond over, you generate a carbocation here. Then you move this pi bond over to make a new pi bond here, and then you have a carbocation over here. So there you go. The next one is a lone pair adjacent to a carbocation. So if you have an atom that has a lone pair on it and it's next to a carbocation, you can take that pair of electrons and dump them into the carbocation in order to make a resonance contributor. If you compare these two resonance contributors over here, why is this one more stable? The reason why is because this one, every atom has a complete octet. Right here, this oxygen has a complete octet, but the carbon doesn't have a complete octet. Whereas over here, the carbon has a complete octet, the oxygen has a complete octet. Also, there's no formal charges here. But the next example is even more interesting because we start with a formal charge and we end with a formal charge. But this one is going to be more stable. And the reason why is because this carbocation doesn't have a complete octet, but over here, everything has a complete octet. Okay? So a lone pair adjacent to a carbocation. Next one, a pi bond between atoms of differing electronegativity. The pi bond electrons can be attracted to the more electronegative atom, causing the pi bond to become unequally shared. And we actually saw this one. We drew this earlier on. So here you can see again, the carbon doesn't have a complete octet, but this is a legitimate resonance contributor. And then the last one are conjugated pi bonds in a ring. So if you have an aromatic ring, both of these represent the same molecule, and that's why a lot of times benzene is just drawn like this, and we'll talk about that more later on. But it's just to show you that those bonds, those pi bonds and the electrons in them are all delocalized. If you think about why they're delocalized, every single atom, every carbon atom rather, in a benzene ring is sp2 hybridized. That means they all have an unhybridized p orbital on them, right? There's an unhybridized p orbital on every single one of these carbons, and it forms a big old conduit around the molecule where the electrons are free to move and they're completely delocalized. And so that's how we can draw the delocalization of the pi electrons in an aromatic ring. Also, you see how the arrows here are going in a counterclockwise fashion. You could draw them clockwise or counterclockwise. It wouldn't matter. You'd get the same result no matter what. All right, well, with that in mind, why don't we take some time to try this problem? And we're going to take a short break and we're going to come back and take a look at it.